Here's just a quick video on 4.5. So we've gone over some of this stuff already. But for a damped mass on a spring, this is the differential equation, which comes about from Newton's second law. Pull out the operator, every quadratic factors. We can't do this by guess and check. We use a quadratic formula. We recognize that the quadratic formula, because it has all these parameters, we can't obviously reduce this to a single number, but a lot depends on the discriminant. Three cases. If the discriminant is positive, then the square root of a positive number is plus or minus some other real number. So you'll get two distinct roots. It'll be overdamped. Both of these roots will be negative. Gamma squared minus 4 omega squared is definitely smaller than gamma squared. So the square root of this is smaller than gamma. So minus gamma plus a number smaller than it is negative. Minus gamma minus a number is definitely negative. So both of these are negative. And you're going to end up with two decaying exponentials. So it'll be something like, x equals, something t plus c2 e is, something else. But both of the exponentials are decaying. No oscillations. In this one, what if the discriminant is equal to 0? Well, then all you have, you have one repeated root, it's minus gamma over 2. So your operator factors into this repeated factor, d minus a minus gamma over 2. So that gives you an e to the minus gamma t over 2. But because this is repeated, you need to come up with another linearly independent function. So this is the stuff we did in 4.3. So I have an exponential and t times that. So this is the general solution for critically damped. This is critically damped. Neither of these has oscillations. So this is the kind of thing where it just, whatever your displacement is, it just relaxes to equilibrium. It doesn't ever shoot past equilibrium. Third case, and this was the topic really of section 4.4. What if the discriminant is negative? If the discriminant is negative, then you're going to have two complex roots. Both will be complex conjugates of each other. A little algebra here. I can pull a minus sign out of this discriminant. If I know that it's negative, I can pull a minus sign out and then pull a minus 1 out, essentially. Get my I. It's quite common to call this the damped frequency. And again, these 2's are just pesky artifacts from not defining gamma as 2 gamma equals c over m. It doesn't really matter though. And so I'll get a real number plus or minus my imaginary component times I. Pop that right into your solutions. You'll have e to the minus gamma t over 2, and then a cosine and a sine. So the conditions, for example, if I were to write down a differential equation just like this is my gamma, this is my omega squared, and so let's see, I have 9 minus 4 times 1, and that is greater than 0, so this is overdamped, right? So I did gamma squared is 9, omega squared, it's already squared, times 4. So for a differential equation, you'll just take these coefficients and you will compare them to one of these three cases. Is it greater than 0? Is it equal to 0? Or is it less than 0?